We're now going to cover numeric integration. So numeric integration includes techniques for approximating definite integrals. So we're going to look at two methods for approximating definite integrals, the trapezoidal and the Simpson's rule. So you might ask, why do we want to approximate a definite integral when the fundamental theorem of calculus gives us a way for exactly evaluating a definite integral by finding an antiderivative for a function and then just evaluating the antiderivative at the two endpoints and taking the difference? Well, sometimes it's difficult or impossible to find an antiderivative for a given function. For example, 1 over x is one of those functions that we can't find a nice antiderivative for. So if we want to evaluate a definite integral, say from 1 to 2 of 1 over x dx, then we're left with actually using approximation methods to evaluate this, since we cannot find a nice algebraic form of an antiderivative for 1 over x. Another reason why we may want to approximate a definite integral is because our function may actually be given to us as a tabulated set of values like we have here. For example, this table of function values may have been obtained from some type of experiment that was done. X might represent time, and f of x might represent something that is changing as a function of time. And so you see we have a table of values here for our function f. So we may still want to evaluate the definite integral, for example, from 0 to 3 of this function, but we don't even really know what the function is. All we know are what the function values are at certain x locations. So in this case, we're also going to have to use numeric integration techniques to evaluate the definite integral. So the first method we're going to look at here is what's called the trapezoidal rule. Now for the trapezoidal rule, we want to approximate this definite integral, and what we're going to do is we're going to divide the interval ab into n subintervals. Each of them will be of width b minus a over n, and we'll denote that by delta x. So down here we have a graphic of what's going on. So the blue curve, that's our function f of x, y equals f of x. And what we're going to do to approximate the definite integral, which in this case would represent the area bounded between the graph of the function and the x-axis, we're going to, as we mentioned, partition ab into n subintervals. So here we have our endpoints determining our partitions. So in this case we have 1, 2, 3, 4, 5, 6, 7, 8 partitions. And what we're going to do is we're going to draw trapezoids underneath the graph of the function. So for example, right here, the first subinterval here, you notice we have a trapezoid right here. And we're going to evaluate the area of this trapezoid along with all of the others and then add up the areas. So let's take a look at this trapezoid over here. So we have labeled here trapezoid T sub I plus 1. That's the I plus first trapezoid. So this might be trapezoid, for example, this would be trapezoid T1, T2, T3, and so on. And this would be the point xi, xi plus 1. So this would be trapezoid Ti plus 1. Now what we want to do is we want to come up with a formula for this trapezoid. Well, the area of a trapezoid is calculated like this. It's going to be the width times your average height. So we're going to take the average of these two distances. Now notice that this distance, the distance from here to here, well, that's going to be f of xi. That's just this height. Similarly, the height of the right side, that's going to be f of xi plus 1. So therefore, this area of trapezoid Ti plus 1 is given down here. So it's going to be the average of those heights, which is right here. We just add f of xi plus f of xi plus 1, divide by 2. So that's our average. And then times delta x. Remember, delta x is xi plus 1 minus xi. That gives us this width down here. So that distance is delta x. And now this can be simplified as, if we think of this as being delta x here, this can be written as delta x over 2 times f of xi plus f of xi plus 1. So that's the area of this trapezoid. Now what we're going to do is we're going to take all of these areas and add them up. Keep in mind now, the area of trapezoid T1, the first one, is going to be delta x over 2 times f of x0 plus f of x1 and then similarly T2 would be and so on. Also keep in mind, this is x0 right here. This point would be x1. This is x2, x3, and so on. So when we add all of these up, here's what we get, and this is going to give us an approximation for the definite integral. So adding up the area of all these trapezoids, you see right here is the area of trapezoid T1. Here's the area of trapezoid T2, T3, and so on, all the way out to the very last trapezoid would be given by this. Now what we'll do is we will factor out a delta x over 2 from each of these terms, and what we get is this. So here the delta x over 2 has been factored away, and then what's left inside is f of x0, that's right here. Now we're going to have two f of x1s. We have an f of x1 coming from this term, and then from the second term. So notice we have two f of x1s. We'll also have two f of x2s, and so on. All the way until the very last term, the f of xn, we only have one of those. And so this gives us a formula then for approximating the area underneath the graph of that function, or for approximating the definite integral. Right here it is. Now the important thing to note here about this approximation formula is that it is approximating the definite integral from a to b. It's approximating this. Now notice when we use this formula, we don't have to find an antiderivative for little f. It just involves evaluating little f at various points between a and b and then adding them up. So it doesn't involve finding an antiderivative at all. And so that's the important thing to note here. Now down here we have our trapezoidal rule stated, so right here it is, it's just what we have up there. So what we do is we just partition AB into n subintervals, each subinterval denoted like this. The width of each subinterval is b minus a over n, which we denote by delta x, and then this is our formula that we found. Now another thing to note here is the pattern of the coefficients. Notice how the coefficients in front of the f terms go 1, 2, 2, 2, 2, and then they end with a 1. So that's your pattern to remember for the trapezoidal rule. And down here we have it. It starts with a 1, and then you go 2, 2, 2, 2, and then you end with a 1. Those are your coefficients that go in front of the function values. That's important to note because we'll also have a pattern similar to this, not the same, but a pattern for Simpson's rule, which is a more accurate way of approximating the definite integral. Now let's take a look at a few examples. So here we want to approximate the definite integral from 1 to 3 of 1 over x dx, and we want to use 6 partitions with the trapezoidal rule, and then we'll compare to the actual value. Well, when we say compare to the actual value, we'll actually just compare it to the value that our calculator gives us back. So what we want to do is we want to partition the interval from 1 to 3 into 6 subintervals. So we're going to have to figure out what are the values x0, x1, x2, and so on. So if we partition 1 to 3 into 6 subintervals, then our delta x is going to be 3 minus 1 over 6, and so that's going to be 1/3. So it will partition like this then. So this will be 1 and 1/3, or 4/3, 5/3, 6/3. In fact, we'll write it as 6/3. It's nice to note it like that. Note the pattern. 7/3, 8/3, and then 9/3, or 3. So now this point right here, the 1 is our x0. That's x1. So those are the endpoints of our subintervals. Now, using the trapezoidal rule then, we simply have this. So it's going to be delta x over 2 Now we're going to evaluate the function at 1 and then each of these points. So it's going to go like this. In fact, we'll write it out just as follows first. So this is what we have to evaluate. Notice our pattern 1, 2, 2, 2, 2, 2, 1. And we're evaluating the function at each of the node values. So now we just have to evaluate this. So this is going to equal 1/3 over 2 is f of 1. Now keep in mind our function is 1 over x. So f of 1 is just going to be 1 over 1. F of 4/3. Now keep in mind 1 over 4/3 is going to be 3/4. So this is sort of nice because basically what we're going to do is we're just going to invert each of these fractions, and that's going to be our function value then. So then what we're going to get is 2 times 3/4. And there we go. So this is what we have to evaluate now to approximate our definite integral. And you can just evaluate this on the calculator, and you'll see that you get 1.106746, out to about 6 decimal places there, and rounding. Now if you compare this to an answer that a calculator would give you, or if you know that the antiderivative of 1 over x is the natural log function, the ln function, you can evaluate this using the natural logarithm, which most calculators will have a natural logarithm button on it. So you can evaluate it like this. Now if you look for the natural logarithm button on your calculator and just evaluate this quantity here, the natural log of 3 minus the natural log of 1, you'll see that you'll get 1 point, and that's rounding to 6 decimal places also. So compare that to our approximation, and you see that our approximation isn't that bad. If we calculate the error, that is the difference between these two numbers, we'll see that our error is approximately 0.00813. So not bad, not a bad approximation. If we wanted to improve on that approximation, we could do several things. We could increase our n here to a larger number, more than 6. Or an even better way would be to actually use Simpson's rule, which would give us a much better approximation, as we'll see in a few minutes. Let's take a look at one more example. So here we want to approximate the definite integral from 0 to 4 of the square root of x using 8 partitions now with the trapezoidal rule. So keep in mind, if we're going to use 8 partitions, then we have to decide what our nodal values are going to be, or calculate them. So x0 is going to be 0, and we're going to go out to 4. So if we're using 8 partitions, then our delta x is going to be 4 over 8, or 1/2. And so then here will be our nodal values. So they'll go, so this will be x0, 1/2 will be x1, 1 or 2 over 2 will be x2, and then we'll have 3/2, 4/2 or 2, 5/2, 6/2 or 3, 7/2, and then 8/2, 7/2, and then 8/2 or 4. So this is x0, 1, 2, 3, 4, 5, 6, 7, and then x8 right here. So then, by the trapezoidal rule, our definite integral will be approximately delta x over 2, so 1/2 over 2. So that's just 1/4. In fact, let's just write that as 1/4. And now we have to do our pattern in here. So it's going to be 1 times f of 0. Now remember, we're using the square root, so our function is, that's our f of x now, the square root of x. So it's going to be 1 times f of 0, well that's just 0, plus, now we start our pattern, 2 times the square root of 1/2, plus 2 times the square root of 1, and so on. And the last one, I don't have a 2 there, we have actually a 1. And there we go, this is what we have to evaluate. Notice our pattern, we have a 1 times 0 to start, so 1, 2, 2, 2, 2, 2, 2, 2, and then we end with a 1. And these are the function values evaluated at the nodal points. And being very careful to evaluate this on a calculator, we get rounded to 6 decimal places. Now let's compare this to the actual value. Now this one we can do by using the Fundamental Theorem. Now remember, the antiderivative of the square root of x, or one antiderivative, is going to be 2/3 x to the 3/2 power. Okay, that's an antiderivative for the square root of x. And then just evaluate that from 0 to 4. And you just get 16/3, which is 5.3 repeating. And if you can compare that to our approximation, you see our approximation isn't that bad, considering that we only used 8 partitions. And if you calculate our error, you see that our error, if we take the absolute value of the difference between these two numbers, we get 0.068292. All right, and so that concludes our discussion about the trapezoidal rule.